Thanks for tuning into this revision zone video. In this video, we'll be looking at standard enthalpy changes, which is part of the energetics topic in year 1 chemistry, A-level chemistry that is, and we'll be looking at the standard definitions and how we can make sure we get the full marks when asked to write these definitions in an exam. Now, you should know already that we are only looking at the changes of enthalpy, not the enthalpies of individual substances. Please go back and look at previous videos if you're not too sure about that. Enthalpy changes can be negative or positive. You can see these in energy profile diagrams. So if you look at our previous videos again, that will help you get a better understanding. So delta, which you should recognize, means change in. Let's get rid of that. That says, it's supposed to say change in. A bit clearer. We tend to follow that up with a little subscript letter. In this case, that means reaction, but that can be swapped with many things like combustion, formation, lattice enthalpies as well. So that could be an L. It can be HYD for hydration and so on, but they'll come up later on. And we're going to look at combustion and formation within this video. But if I have a reaction which I can't define directly, we tend to, by either combustion or formation or any of the other ones I've mentioned, we tend to use R as generic. We tend to also see this. Now, this is very important. This is a lowercase theta symbol, but it means standard conditions. Now, standard conditions, you must know them, and there are different criteria or different conditions that you need to learn. Some obvious ones you might be thinking of or may already know is temperature. Temperature is at 298 Kelvin or 25 degrees Celsius. I recommend you use 298 Kelvin because that is the standard unit for temperature and typically one that we use. Know that there's a difference of 273 between these two scales. Again, a very important calculation or manipulation of data that you need to be able to do. So that's standard temperature. We have concentration. This is short for concentration, and that, you may have guessed, is 1.00 moles per decimeter cubed. So if we have any solutions within our reaction, they need to be standardized at 1 molar. Pressure is typically quoted at 100 kilopascals. 100 kilopascals, you might see 101 kilopascals. You may even see 1 atmosphere, 1 atm. These are all standard units of pressure. You may see 101, very rare, you see 101 in some places, but 100 kilopascals and 1 atmosphere is definitely a learn. If you're at Excel, 1 atmosphere does come up quite regularly. Now, this also means standard conditions and states. So what we need to consider are also the states. Now, obviously, the states change depending on the substance you're looking at. Now, if I'm looking at carbon, we typically say that's solid. If we say it's oxygen, it's a gas at these temperatures and pressures. So the state that we write down during these calculations or in these equations are the state that they would be most stable in within these temperatures, pressures. Okay, so this is the state. The substance is most stable in at 298 Kelvin and 1 atmosphere, our standard conditions up here. Okay, this descriptor here represents this delta RH or delta HR is is a descriptor for the standard enthalpy change of reaction, or standard change of enthalpy of reaction. And I'm just going to change colour pen here. So what we are looking at is the standard. So we're talking about this descriptor here. This is the standard enthalpy change of reaction. So we just want to get rid of that. RXN is short for reaction, and the definition for that the definition for that is the energy transferred when molar quantities and I'll come back to this idea of molar quantities of a substance we can say reactants here, in fact, stated in the equation stated in the chemical equation, that is react under standard conditions. So react to standard conditions. Okay. Now, what we also need to look at is this idea of molar quantities. In any description, so if we look at molar quantities here, we always, or any definition, we'll always look at 1 mole. And that's really, really important. 1 mole all the time. 1 mole all the time. So what we need to be careful of is that when any definitions with the other ones that we're going to look at, we must incorporate 1 mole. So that's what it means by molar quantities. The other thing that's really important, the unit for any enthalpy change, whether that's delta HR, delta AC, delta HF, or so on, is always kilojoules per mole. Okay, it's always kilojoules per mole. Right, our next definition is enthalpy of combustion. Now, enthalpy of combustion is always delta CH. Now, you might see delta HC, you do see that in text sometimes where the C is after the H, so don't worry if you do see that, it's still the right, still correct, but you tend to see this descriptor more often now. Now, we need to know the definition for this, so we'll do that in red. So the definition for this is the energy. Now, it's a combustion reaction, so it's exothermic, so it's always going to be released. You can put transferred in if you want to. The energy released, if you're unsure, use transferred. The energy released when 1 mole of a substance is completely burned or reacted in oxygen under standard states and conditions. Right, and again, you can see 1 mole here, really quite important, that it appears because there's always a mark to say 1 mole of that substance is burned. Now we can just go through some examples of reactions which are represented by this enthalpy change. We're going to look at some simple ones, some common ones to begin with. The first one we're going to look at is carbon. Now carbon is solid. It's the most stable state of carbon. There are many forms of carbon though. There's solid carbon, could be diamond, solid carbon could be graphite, solid carbon could be Buckminster fullerene, or coal even. Now, when it comes to enthalpy calculations, or thermodynamic calculations, we tend to use graphite. Okay, we tend to use graphite. So if you're looking up a data book, always try and use the graphite one unless otherwise specified. In exam papers these days, they don't tend to get you to find these values anymore. They tend to just give it you in the actual question itself. Now we're going to react that with oxygen gas. Okay, now this here is going to give us, because it's complete combustion, carbon dioxide gas. So this, I can describe this reaction as the enthalpy of combustion, the standard enthalpy of combustion of carbon solid. Okay, and remember this is going to be a negative value because it is exothermic. Now, the other example we can use is hydrogen gas, oxygen gas. That gives us water, liquid, standard state. This is the state of water in these conditions at the top that we have, forget the concentration, but the temperature and pressure as required. So basically referring back to this statement here. In terms of this, the descriptor would be delta CH, standard hydrogen gas. Now, you must always check for balanced equations. The top one here of carbon was balanced, but we need to make sure we balance this one, and it's quite simply, we need a half O2 there. Okay, so I might just do that again. It's a little bit clearer. So a half O2. So it's got to be balanced. We want to try and keep it to 1 mole here. Try and avoid doubling up. Don't put 2, 1, 2 there. Try and 2 here. Try and keep this as 1 mole, like as we have with the carbon. Always try and do that, because these are always for molar substances. The other thing is, just be mindful of this here. If in an exam they give you an equation, they say describe why the enthalpy of this reaction is lower than expected. When they say lower, it tends to mean more endothermic or less exothermic. So it's a small value. And you might want to look to see if it says gas here. If it does say gaseous here, it's no longer standard enthalpy change. It's because what we've got now is we're using some of the energy from the combustion reaction to vaporize the water. So therefore, that's why our overall enthalpy value becomes more endothermic or less exothermic. Another example I'm going to use is carbon monoxide. Now, carbon monoxide is a gas. I can react that with oxygen gas, and that will give me carbon dioxide gas. Now, again, I need to balance, and put my half there, and my descriptor is delta CH in brackets. I've kept this as 1 mole of carbon monoxide. So I'm going to put that in the square brackets. And again, because it's 1 mole, I'm quite happy to just write that in. We want to try and keep this as 1 wherever possible, so don't double through. Now, I could also say, well, look, if I give you a descriptor, I want the enthalpy of combustion of, let's use methane. It's a common fuel that is used. So it's for the molar quantity of the methane, 1 mole of this. How would I write it? Well, first of all, I need to write the equation, the balance symbol equation for combustion of methane. Again, keeping this as liquid, you need to balance it. When I'm balancing it, try and leave this by till the end. Don't balance this until you absolutely need to, the oxygen, that is. Now, so I've got 1 carbon, 4 hydrogens, 2 hydrogens. I quite simply need a 2 there. That gives me 4 oxygens, and therefore I need a 2 there. That balances that equation. Fortunately, I've only got 1 mole in front of here, which I don't need to put in, but I'm just going to put in to show you. So that satisfies molar quantities from the previous definition, and the current combustion definition as well. It has to be 1 mole. Really, really quite important. Don't forget that. Do not start doubling up things. If this was 2.5, for instance, try and keep this at 1 mole. So that's definition of combustion. We want to now look at formation. There we go. Right. So enthalpy of formation can be also written as delta H, or delta F, I should say, H. You can put delta HF as well. Like I've said, standard symbol, standard states conditions, that's there as well. We want the definition. Definition is a little bit different with formation. We don't tend to see these reactions in the lab, so to speak, or you may not have come across these reactions typically in your chemistry course so far. But the definition is now the energy. If you're ever unsure, just write the energy transferred. Tends to be exothermic in this one, but we'll just put transferred. Transferred when 1 mole of a substance, it's essentially the same as above, but this is where it changes, is formed. Let's get rid of that. Sorry, is formed from its constituent elements, and I'll come back to constituent elements in a moment, and what that means under standard states and conditions. Okay, so that's definition. Again, we've got my 1 mole. Got my 1 mole, must be in there always. So make sure that's included. 1 mole of substance. I'm forming this 1 mole of a substance. Now, what does constituent elements mean? Well, that basically means, how would I find the elements that are used to make this 1 mole of a substance at standard states conditions? So we kind of covered this before. So carbon would be solid. Oxygen would be O2 gas. Hydrogen would be H2 gas. So you've got all your diatomic, you've got N2 gas, and so on. Neon will be singular. That's how it's found. So if we were to do a reaction with neon, however unlikely that is at this stage especially, it would come up like so. So just keep that in mind. Metallic substances always just monatomic. In this case, we have to put them as, even though they're lattices, we're still going to put them as single atoms here. We could use mercury, for instance, but this time it will be liquid. But these are the standard conditions and states they will be in. Now, the examples of this. Now this time I'm not going to give you the equation, we're going to go for the descriptor first, and then try and formulate the equation from there. So if I look at delta F, and we're going to come up with some common ones, and the most common ones are like the ones above. So let's start with carbon dioxide gas. Now that means, in fact, we can get rid of that arrow, we don't need that. I'll just change the pen. Right, so I want to form 1 mole of carbon dioxide. That's what we're looking at in the definition, 1 mole of a substance. I got to think, what elements make those substances? The elements that make those substances are carbon and oxygen. What states and what kind of molecular structure will they have? Carbon's solid, singular, oxygen, diatomic gas, gives us carbon dioxide. And I want to try and keep this again at 1 mole because that's how it's represented in our definition. In this case, this is balanced, so I've got nothing to do here. Okay, nothing more to do, at least anyway. If I was to do, however, the formation of H2O and liquid, then what I need to do here is where I'm making 1 mole of water. Let's just put the water in first this time. And I'm going to make that from its constituent elements. Its constituent elements are hydrogen, but hydrogen hangs around in pairs. And oxygen hangs around in pairs as well. Now, to balance this, I need to put half there, and that's the formation of water. You can actually see that this is exactly the same as the combustion of hydrogen up here from our combustion examples. There's no difference between them. They'll have the exact same values. So if this was minus 120 kilojoules per mole, for example, so will this be. It's just I will use them as I need them. If I need to use it as a combustion, I'll use the delta C descriptor. If I want to use it as a term of formation, I'll use the delta F. But this doesn't work for everything. It's just convenient that this is the case. And that also goes for the combustion of carbon. It's the same as the one above here. So these two enthalpy of formations are exactly the same as enthalpy of combustions. However, if I then change that, we look at something slightly different. The enthalpy of formation of carbon monoxide. So this is where it changes slightly, in the sense that it won't be the same as the combustion of carbon monoxide. I want to form 1 mole of carbon monoxide. Its constituent elements are carbon and oxygen. Carbon is a solid, plus oxygen, which is diatomic, and it's a gas. I need to balance that out, which means I need a half here, and that balances this equation out. Now this is nothing like the combustion of carbon monoxide we saw earlier, the enthalpy of combustion. So be very mindful of that. This is just purely the formation of 1 mole of carbon monoxide. Let's do one last one, and this last one is a little bit more complex than the ones that we've looked at, but it's a very, very common one, and it's something that you do need to be able to do, is ethanol, liquid ethanol. So again, we don't change the way we tackle it. We want 1 mole of C2H5OH. Hopefully I've left myself enough space there. Let's see. That is made from carbon, solid, hydrogen. Now we know hydrogen is diatomic and it's a gas. Got enough space, and oxygen. That's a diatomic gas as well. I haven't left myself space here just in case I needed to put a number here, but hopefully we won't need to. We can keep it as 1 mole, which we will be able to in this case. But you know, if you're wondering why I haven't left the gap, it's because I intend to keep it as 1 mole. Let's balance this. I will use just a different color pen here, maybe just to highlight that a little bit. So again, I've got all its constituent elements in their standard states and conditions. I have 2 carbons, put 2 there. I have 6 hydrogens, so I'm going to put a 3 there, so that's 6 hydrogens on either side. Oxygen, I've only got 1 oxygen, so I want to put half there. So this is the reaction that determines the enthalpy of formation for 1 mole of ethanol. Okay, and we could go on to do quite a few. We could do it for any substance that we like, and there's many more you could try. You could try with methane. So if you want to pause the video and give it a go with methane, the enthalpy of formation of methane, you can do that now. So I will just write the descriptor here. And you can pause the video now and give it a go and then see what or whether you get the right answer or the right equation. Right, so hopefully you've had a chance to have a look at the equation for this. Again, we don't change our tact on this. We still write that we want methane. We look at the elements here. It's carbon, solid, and hydrogen, gas. And it's diatomic. Got to make sure it's diatomic. Then we just go about balancing 1 carbon, 4 hydrogens, 2 hydrogens, stick a 2 there. And that is the enthalpy of formation for methane. So the definition of enthalpy of neutralisation is as follows. As neutralisation says acid and base reactions, we need to make sure that we have a descriptor for that as well. The descriptor is a triangle. Neutralisation, so we use N for the descriptor here. And again, it's in units, obviously. Let's have a look at the definition. Now, the definition here is when, so we always look at it from the acid point of view in this particular case. Remember, it's acid plus base or alkali. We'll tend to look at alkali because, in fact, let's just only use alkali because we need the production of water here. In fact, let's just make that a bit better, a bit more clearer. And that gives me a salt and water. So the definition here is when we neutralize completely an acid with a base or alkali, but we're going to use alkali here, to form 1 mole of water, and that's where that 1 mole comes in here. So it's the energy transferred when 1 mole of water is produced when an acid is completely reacted or neutralized, I guess you can say, with an alkali. I'm just going to move this up a tad. The way we can describe that is quite simply, for instance, I can take HCl aqueous as an example, sodium hydroxide is another example, and that produces sodium chloride aqueous plus H2O liquid. So for instance, I'll give you the enthalpy of neutralization for this particular reaction here is minus 53.7 kilojoules per mole. So I've just taken that from a textbook as a quoted value. That's the enthalpy of neutralization for this particular reaction here. Now, if we look at this, we need to make sure it's balanced. It is balanced. We don't have to do anything. There's 1 mole of water being produced. And in fact, if I take this a bit further, there is a common question of why the enthalpy of neutralizations are typically very similar. So in order to kind of give that explanation and that answer, we need to break this down into its ionic equation. So that means, as you've seen before, you break up only aqueous ionic substances. In this particular case, we've got H+. I'll do this quite quickly, or as quick as I can. Cl- aqueous plus Na plus aqueous. I'm just going to continue underneath. Hydroxide ions, aqueous, gives you Na plus aqueous plus Cl- aqueous plus H2O liquid. Now we remove the spectator ions. Spectator ions are chloride because they have neither changed oxidation number or state. Sodium still +1, same oxidation number and same state, leaving you with the following ionic equation. Right, so it gives you hydrogen ions plus hydroxide ions gives you water, H2O, 1 mole at that as well. Remember, this is kilojoules per mole of water being produced. That's how much energy is being produced. Now, if we're looking at acids and alkalis, which is why we have to look at alkalis because that's the one that produces water, we will find that any reaction I have, so if I change this reaction up here, I will just do this in green. Another example, you go H2SO4 aqueous. I'll change the alkali to potassium hydroxide. That will give me K2SO4, which is potassium sulfate salt, plus water. We need it to be balanced, and that's liquid. Remember, I'm keeping my state symbols in there always. So in this particular case, for instance, we need to make sure it's balanced. Like I said, put 2 here, just 2 potassiums. I've got 4 hydrogens on this side. Oops, 2 here, and I've got 6 oxygens on this side and 6 oxygens, so that's now balanced. If I was to write the ionic equation for this, I would quite simply end up with, just going to skip straight to the ionic equation. I'll mention the spectator ions in a moment. And 2H2O, which simplifies down to the same H plus aqueous plus OH minus, oops, that's minus aqueous, giving you water, which is exactly the same as what we have initially. So why would, if that enthalpy up here is for that ionic equation, why would it be any different to this? Because remember, it's per mole. I know we've got 2 moles of water here, but we've simplified that down to 1 mole. So we can safely say that the enthalpy of neutralization for this particular reaction here will be approximately minus 53 kilojoules per mole, or minus 54 if you like, but somewhere in that region. We'll have it somewhere in that region. The spectator ions here are my sulfate ions, potassium ions, so I can get rid of those, and that leaves me with the following. So I hope you found that video useful, and it concludes the standard enthalpy definitions that you need to know. And if you want to see more, please use the comment sections to say which topics you would like to see. We'd be happy to try and provide them. And of course, hit the like and subscribe button. And thanks for watching, and we'll see you next time.